Hi. So it's really great to be here, although I'm a little bit jet lagged. And I'm also confused because there are a few people I saw last week in Berkeley, and now I see them here, and it looks to me like some sort of a mathematical contradiction. So it's really wonderful to celebrate Nati's birthday. I know Nati since the late 70s. Where Nati was a PhD student, I was a master student with Micha Perles. So what I remember, and then you can chronologize it, is that at that time Nati didn't have a beard, but only a mustache. And so he looked, what?
And you did have a beard.
No, I also didn't have a beard. I had a strategy to switch every war. At that time, I couldn't even grow a beard, but I used to change every war. So the last time I changed was in the Gulf War. But at that time, I didn't have a beard. From having beard, not having beard. And Nati, I think you were a soldier, so he was a, sort of Nati was my oldest brother. Okay, so there are also some even older academic brother, Meir Kachalski and Michael Kalai. So Micha Perles was really specializing in Kalais, but they left home already. So Nati was my older brother, and I see the dynamics like in my own children. So my older daughter Neta, usually she tells the other children what to do. And usually they rebel and they argue with her, but 90% of the time they eventually do what she says. And this is more or less the dynamics between Nati and me. I always argue with him. Sometimes it really drove him crazy, so this is time to apologize for all these years of arguments. But eventually I do what he says. So I will tell you a few things. So I will tell you a few things related to, essentially to the old days and some new things. And also I should say that I generally like to dream other people dream. I know there is a famous theorem in polytope theory which is called that polytopes are shellable, and it was proved by Brugesser and Mani. And once I asked Mani, how did he prove this theorem? And he said that actually one night he slept and he dreamed the proof. And this was very nice, except what was the role of the other co-author? So I said, very important. And okay, but over the years I really like to dream other people dream. יש לי טלפון בכיס. דווקא יש לי טלפון בכיס שהוא לגמרי יוסלס. אתה יכול אולי גם לסדר אותו? Okay, so in general, I like to dream the other people's dreams, and maybe I will tell you, I know some of Nati's dreams, and sometimes we share the dreams, or we have conflicting dreams about the same problem. So I'll tell you a little bit about it. So, but let me start with something that we started again in the late 70s, early 80s. And I remember a talk that Nati came to. Where is the black marker? There was a black marker. Well, okay, I don't. So come close if you want to see anything. So it is related to a lecture by Nati. He came, which was entitled like this. You remember this lecture?
Except it's tough and not that.
Okay, this is again quite typical. You see everything. What was it?
Tough, it's tough and tough.
לא, סליחה. Hipper somehow was left in English. So in English it says an ignorant boy got lost in a hyper forest. And this is related to some of the old things where we were both influenced by. I should also say that probably Nati is the person who influenced my own career the most from all the people. But I don't know if for the better or the worse, but in some sense, this question has no meaning because it would be a different person if without Nati's influence. But in this case, we were both influenced by some questions that were posed by Micha Perles. And let me tell you what was Micha's theorem. So Micha proved the following theorem. So let F be a subset of N choose K. So F is a family of K subset of an N-element set. N is the numbers 1, 2, up to N. And suppose that such that for every S subset of N, S of size K minus 1, the number of T in F so that T contain S is not 1. Is not 1. So another way to say it, it's either 0 or greater than equal to 2. So this is a theorem. I think this is Perles. 70. Then the size of F is less or equal than N minus 1 choose K minus 1. Okay, so this is a nice theorem. So again, you want a family of K sets, and you want the property that every set of size K minus 1 is included either in no set in the family or in more than 1. Now, how do you prove this theorem? Let me just let you look. So the proof is a simple linear algebra proof. Look at the matrix. This is the matrix over the. Yeah. So you find the counterexample after all these years? What? You know, everything is tentative in our business. You know. Oh. Okay, let me just give you an example which achieves this. So if you take all the set S, all the set T, so that 1 belongs to T, then the set of all K sets which contain a fixed element, the number is N minus 1 choose K minus 1, and they no, maybe I said something. No, I think it's okay. So. No, so okay, we will figure it out quickly. First of all, this is the example. This is the extreme example, or one of the extreme examples. Maybe I had something wrong. No. Well, I told you I'm a jet lag. Okay, sorry. No, I simplified. Yeah, but, okay, sorry.
Most likely it's not.
Right, okay. Sorry, I oversimplified the matters. Let me state the theorem again. Let F be a subset of n choose k, and suppose that the size of F is greater than n minus 1 choose k minus 1, then there is a F prime in F such that for every S in N, S of size k minus 1, the number of T in F prime, T greater than S is not 1. Okay, sorry. This is the statement. Let me repeat it. So whenever you have a family of k subsets, if the size of the family is greater than n minus 1 choose k minus 1, then you have a subfamily so that for every set of size k minus 1, the number of sets in the subfamily containing it is different than 1. And if k is equal to 2, then this another way to say it, that if you have a graph with more than n minus 1 edges contains a subgraph with a minimal degree greater than 1. Actually, we know that it contains a cycle. So this is the theorem. Okay. So how do you prove this theorem? You look at the... Yes?
F prime non-empty?
Sorry?
You want F prime to be non-empty?
F prime non-empty.
Yeah. So, okay. You know, when we reach this time of details, then I feel more comfortable. Yes. Okay. So you look at so the proof is the following simple proof. You look at all the k subsets in F, and here you look at all the k minus 1 subsets of n. And now you look at the incidence matrix, matrix. And then there are a few things you have to notice. One thing you have to notice is the rank of this matrix. The rank of this matrix is less or equal to n minus 1 choose k minus 1. So here altogether we have n choose k rows, but there are some linear dependencies. So every time you have every time you have a row which corresponds to a set S, so that the index n choose k minus 1 rows, but there are some dependencies. Every time you have a row which corresponds to a set S which contains the element n, then this row is a linear combination, or is the sum actually of rows corresponding to sets which do not contain the element n. So this is it's an easy effect that the rank is at most n minus 1 choose k minus 1. And on the other hand, this implies that if you have more than n minus 1 choose k minus 1 columns, so if you have a hypergraph with more than n minus 1 choose k minus 1 sets, then there is some linear dependency. So there is some linear dependency. So you have some columns which sum up to 0, and this precisely corresponds to cycles in the case of graphs. So you have here some columns which sum up to 0, and what does it mean that they sum up to 0? It means that every k minus 1 set is included in an even number of them. So if every k minus 1 set is included in an even number of columns, those columns which sum up to 0, they correspond to this hypergraph which violate which violates this condition. And actually, what this theorem tells you that you can replace here the not equal 1 by 0 modulo 2. So if you have a family with more than n minus 1 choose k minus 1 elements, a family of k sets, then you have a sub hypergraph so that every k minus 1 set is included in an even number of sets. Okay, so this was the argument of Micha Perles. And you see it has a very nice, this fact extends the fact that a forest contain, so you can think about families which satisfy this property as some sort of hyperforests. So this is one of the ways to think about hyperforests, and this is some sort of a high-dimensional analog of forest, and this is related to one of Nati's recent frontier, maybe the most recent, which is high-dimensional combinatorics. Of course, Nati moved high-dimensional combinatorics in high dimension in many wonderful directions. So I'll just mention a few of them. Some of them related to extensions from graphs to higher dimensional objects, but some of them relate to other things like multi-dimensional permutations. So you can think about a permutation as a matrix of 0 and 1s, where in n by n matrix of 0 and 1, where in each row there is 1, 1. If you just extend this definition to higher dimension, to 3 dimension, to 4 dimension, to 5 dimension, then you get new objects that apparently were not considered before, or at least not in higher dimension. And this is high dimensional permutations that Nati and Sue studied recently. And another things which is very natural, but only was studied by Nati and Roy, initiated a few years ago, is the study of random hypergraph or random simplicial complexes. So the high dimension analog of the Erdős-Renyi model, and there are even the very basic property of connectivity that Erdős and Renyi studied in their first paper was extended by Roy and Nati to higher dimension to understand when a complex, simplicial complex is connected. And another notion that again could have been this very natural notion is to understand what is the right extension of the notion of expander to higher dimension. And again, Nati and Roy has a homological definition, which is very natural. It was, I think it's a little bit implicit in their paper, but it's clear that this is a definition of expanders in high dimensions. It was rediscovered by Gromov maybe 4 years afterwards, and it is a subject of extensive studies now. So high dimensional combinatorics in really a very wide horizons is something that Nati is interested in recently. But let me go on to tell you a little bit about things related to these older things. So this is the theorem. Actually, Micha Perles asked a question already then. He asked, okay, so there was one development regarding the proof that Nati achieved in his postdoctoral years. And you see here, the study of the rank is fairly simple. But you can ask yourself, suppose you look at a matrix where instead of k sets and k minus 1 sets, you look at k sets and R sets. So you look at this incidence matrix. So you look at the incidence matrix of k sets versus R sets. Well, R is smaller than k. And you ask, what is the rank? What is the rank over Z2? So in the case of when R is k minus 1, it's easy to see that the rank is n minus 1 choose k minus 1. But in general, this is both a very natural question, and it was solved completely by Nati and Bruce Rothschild when Nati was a postdoc. And the answer is fairly complicated, or not so complicated, but it requires, there is a formula. And then it was extended in another famous result by Wilson, right? By Wilson to other characteristics. And so this is a very nice direction, which I think came from this, or at least related to this old proof of Micha. Another question that Micha asked is what happened if instead of 1 here, again, perhaps not in this language, you say greater than some other number m. Oh, you know what? Let's take another variation. You leave it that it's not equal to 1, but instead k minus 1 here, you replace this by k minus, replace it by r. You place this by r. Okay, so this is another question. And this tells out, both this question and its extension came from a certain generalization to Halley's theorem that Micha Perles studied with our even older brother, Meir Kachalski, when he was, when they worked together. And they had they studied the Halley type theorem. I will not describe the connection to Halley type theorem here, but they studied what happened if you, instead of k minus 1, you ask about k minus 2, k minus 3, and so on. And you see that actually, and here there is a very similar conjecture, but instead of, you get some binomial coefficient. So n minus something. So you choose r, or n minus k plus r, or something like that. Choose r also. Okay, so there is some very natural conjecture, and you see that the computation of Nati and Bruce Rothschild give you some bound, but this is not the right. So this is very important result on its own, but it's not the right bound. It doesn't give the sharp bound for this question. And indeed, this was the topic of my PhD thesis, or the first question I dealt in my PhD thesis. And eventually, the solution that I found was to look at other incidence matrices. So not to look at incidence matrices over Z2, but to look at some incidence matrices over R. And here, instead of 1s and 0, to put some other quantities which come from some subdeterminants of some determinants. So there was some recipe to create an incidence relation between K sets and R sets, where instead of 0s and 1, you use some other numbers. And this allows you to decrease the rank as much as possible, so it meets the bounds which will settle Micha Perles conjecture. So this is one place where our road intersect in our very early younghood, and there were some nice development. I should say there was another nice development at that time, which is related to some later work by Nati. So one thing both of us noticed is that this question extends for k equal 2, it extends the notion of forests and trees and acyclic graphs and so on. And we were both wondering what is the higher dimensional analog of trees. And so one thing that I tried to do is to count these higher dimensional. So I didn't know what they are precisely, but I wanted to count them. So count high dimensional trees. And actually, I was not the first who had this idea. And there was a few years before, Eitan Bolker also had this idea coming from some transportation polytopes. And he counted them, and he conjectured even, well, I didn't know about his work, but he conjectured a formula. So as you know, the number of trees is n to the power n minus 2, and you both Bolker and I conjecture that when you move to higher dimension, you get n to the power n minus 2, choose k minus 1. Choose, okay, so this is k subset, yeah, so it's k minus 1. Okay, so he just checked this conjecture for 3, 4, 5, it was okay. For 6, it was wrong. And then he wrote a paper and said, this conjecture is wrong. And okay, but I had a more, I don't take no as an answer. And actually, and it turns out that, okay, so if you consider, okay, so this, for those of you, this incidence matrix correspond to the homology, of simplicial complexes. And it turns, so one notion of a hypertree or hyperforest, but let's say hypertree is a cyclic complex. A cyclic complex. A cyclic complex is a complex that all the homology vanishes. And so a tree is a one-dimensional complex that all the homology groups are vanishes. And you can talk about the cyclic complexes in higher dimension. And it turns out that if you count the cyclic complexes, so if you count the cyclic complexes where the coefficient, where the ring of coefficient is Q, so these are called Q cyclic complexes, then you get the number n to the power n minus 2 choose k minus 1, but you need to change the problem. And the way to change the problem is you count Q cyclic complexes so with weights. Now, if you add weights, it really helps a lot to achieve the outcome you want. Okay, but you don't, one way is just to add one weight, which is this one, to one such object, but this is a little bit...
Did you go to Bible experts to ask what the most common weights are? And then...
So the weights that you need to add is you have to count every complex k according to the dimension of the k minus 2 in this homology group, square. So if you give the right weights, then you get a nice formula. And so this was actually my first result from my PhD period, which eventually, which I published in the early 90s. Oh, I should say that what? Early 80s. Yeah, early 80s. Yeah. Usually I mean to say 90s, I say 80s. Now that there are videos, you see how you speak, and it's terrible. I mean, really. But not even English mistake. Just anyway. So another thing that Nati and I have in common is that we both have publications when we were teenage in the same journal, which is called Gilionot leMathematica. So I think Nati's first paper is from when? 71. So you see this title of the 68. Yeah, I mean, the title 40 years of combinatorics of this conference is a lie because Nati started to do combinatorics maybe 45 years ago or something. Yeah. Anyway, okay, so this is one nice thing. And recently there is a paper, there is a very nice construction by Nati, Roy, and Michael Rosenthal, and they build a large number of such creatures, cyclic complexes, and the construction goes as follows. You look at all subset A in 1 up to n, so that the sum of elements in A is either A or B or C. So you pick 3 numbers, A, B, and C, and you look at all the triples so that the sum of elements modulo n is either A or B or C. Now this gives you, you can do it in higher dimension, but this gives you a collection of n-1 choose 2 triples, and miraculously, this collection is always a Q acyclic complex. And the way this happens also involves things that it involves both homology computation and somehow it involves Fourier analysis. So to prove this, you need to do Fourier analysis, and this is a very nice construction. So I was very enthusiastic when they talked. I think I was even more enthusiastic than the authors of this of the paper, but this is very nice. And recently, Nati with several co-authors studies the combinatorics of these higher dimensional simplicial complexes, and there are all sort of magical behavior which is very, very different than the behavior of graphs. Yeah, okay. So let me, so this is the first part of my talk and almost the last part of my talk. Okay, let me mention a few. So what I want to tell you, the other thing I want to tell you about some dreams of Nati and my analysis of these dreams. And then I want to tell you a little bit about influence. So suddenly the place where my connection with Nati is the strongest is in the study of influence and the discrete Fourier analysis and these kind of things. And I will mention one problem about influence of large sets. Okay, here are some dreams. To find, there is a famous Moore bounds for graphs with d-regular graphs with large gears. Okay, the Moore bound, so gears, I hope everybody know what it is. D-regular, you know, I can give you a wrong definition anytime, but maybe it's better you keep your knowledge. So you look at graphs, d-regular graphs of gears G, and there is a very simple bound, which is, you know, just counting. And it's not clear if this bound is asymptotically tight or not, you know, on some logarithmic scale. I think Nati believes it's not tight, right?
Yeah, bound on what?
Bound on the number of vertices of a k-regular graph, d-regular graph of gears G. What is the minimum number of vertices? So it is 1 plus d-1 plus d-1 squared. It's at least plus d-1 to the power g over 2. This is a lower bound. And the big question is this lower bound tight asymptotically in certain sense? And there is a random construction which gives you something which comes close, but about half of it. And the Ramanujan graph gives you something which go 4/3 over. So there is a parameter. There is a parameter 1, and there is parameter 2. 2 correspond to the Moore bound. 1 corresponds to a random construction. Ramanujan graph gives you 4/3. There was a short period that people claim that they can move even forward. And the big question is, can you reach the Moore bounds? I think Nati believes you cannot reach the Moore bound. Okay, so here, and this is trying to push this problem forward is a long-term dream of Nati. I don't know. What? And many, yeah, I don't know. I want to ask Michal if Nati wake up and talk about the Moore bound, but anyway, so this is one thing. Another dream of Nati is to improve the upper bounds for error-correcting codes. So error-correcting codes is a wonderful theory with huge applications of mathematics. The question is, what is the upper bounds for the size of an error-correcting code, which corrects, say, so a code is so let's say correct alpha times n error or minimal distance alpha times n. So the best upper bound is called the MRRW upper bound. It was proved in the 70s. It uses the linear programming method, so it can be presented in terms of Fourier analysis of the characteristic function of the codes. It can be presented in other ways. And it's quite amazing that since the 1970s there was no improvement, not for this problem, not for the analog problem for spherical codes. And I think a long-term dream, which this case I also share this dream, is to improve it even a little bit. At some point we work on it together, but we couldn't push it not a single bit. Another question is the...
Alex says it better. I mean, a new proof for the MRW.
Yeah, Alex is certainly, you know, there is a lot that was done using about error correcting code, about using Fourier analysis, about error correcting code. Alex did a lot of things. Where is Alex? He's not here. Oh, here is Alex. Yeah. Okay. So another thing is designs. Okay, a design is a collection of k sets, so that every k-1 set is included in a single k set. So you have n elements. You want to find k sets of size k, so that every set of size k-1 is included in one set of size k. So if n satisfies some natural divisibility property, such creatures can exist. Remember, the first time I was abroad with Miki Tarsi, we spent a month together, and we had very long courses about designs. And Miki wrote a story about ants and sent to his children. So this was very nice. And this is one of the most important questions in combinatorics. Most people, and I am one of them, believe...
You didn't mention any question. You say this is the most...
The question is if such things exist.
Okay.
And you know, I, like most people, believe that such things exist. Maybe there are some conceptual barriers why we cannot construct them, but it seems that it's quite obvious that they exist. And Nati is one of the few people who believe that they don't exist. I don't expect that this disagreement will be resolved. Like our political disagreement, they will simply not be resolved. We'll continue to disagree. Nothing. Okay, so another dream of Nati, very early Nati tried to involve computer science and game theory. Again, this is related to the things we did together about influences, and also it had a lot of impact. So let me mention one problem just to end, and this is the problem of influence of large sets, and I will just mention the problem without referring to influences. So here is the problem. Hopefully this time I will formulate it properly. In this problem there was some movement recently. So here is the problem. F is a family of sets, of subsets of 1 up to n. And the question is, what is the minimum size of f that guarantees the existence of t in 1 up to n, t of size n over 2, such that the trace of f on t is greater or equal to 3/4 times 2 to the size of t. Okay, the 3/4 is just an arbitrary number. Okay, so we want, and what is the trace? Just to remind you, the trace of a family on a set T is the set of all intersection, is S intersect T, so that S belongs to F. Okay, so this is the question, and I should mention, this is sort of a natural and nice question. There is a famous theorem. If you want to achieve a complete trace, or in other words, if you want the family to shatter the set T, then there is the precise bound, which is known as the Sauer-Schellach theorem. And the precise bound that allow to shatter a set is n choose 0 plus n choose 1 plus n choose r plus 1, where r is the size of the set. So So you see that if we want to shatter a set which is some fraction less than half of all the elements, then it's very easy. Then this is very easy. But the question is, what is the size of the family which allows us to achieve a trace which is at least 3/4 times 2 to the t? And here there is a theorem. So what is known? So it follows from a theorem by Nati, Jeff Kahn, and myself, which is often referred to as the KKL theorem. It follows that f of n. Okay, what is the minimum f? So let's denote this by f of n. So it follows that f of n is less or equal than 2 to the n divided by n to the power c, where c is a small constant. So it follows from KKL that if you have a set of size 2 to the n divided by n to the c, then you can almost shatter or fractionally shatter a set of size n over 2. Actually, this can be even a larger set of size, I don't know, 3/4 or whatever. But let me just concentrate on this question. So this is and for a long while, and this question is equivalent to a question about influences of large sets, but I will not define the notion of influence. And for a long time, there was no movement on this problem. Now, recently, so Jeff Kahn and me. So I think we proved, okay, so we didn't state it precisely this way. I'm not entirely responsible, especially Jeff is here, he can correct me, that f of n is greater than 2 to the n divided by something exponential in n to the alpha, where alpha is smaller than 1. So it's not enough to have a set, of size 1.9999 to the n. So actually, we didn't study precisely traces of n over 2, but I think what we did really do this. And even more, so this was in 2013, I think more or less. And then even more recently, Bourgain improved the consequence of KKL and showed that f of n is less or equal to 2 to the n divided by n to the c. But this time, this was small c, and this is a capital C. So this is for every c. Okay, so this is better. But still, there is a huge gap between so there was some progress, and when we work on it, we thought that we just cleared the whole area. Well, okay, I thought. Because somehow the two concrete questions that were posed, we solved them. But then it looked that actually, okay, so it looked to, then I realized, I mean, Jeff realized it all along, but that really there is still a huge gap between what is known and what can be proved. So hopefully next time for Nati's next birthday. Actually, I noticed that in Nati's birthday conference, one difference between this conference and other events is that Nati doesn't ask questions. Usually, in Oberwolfa, the tradition is the Israelis, Noga, Nati, they sit in the front and they ask questions all the time. And this time, Okay, so maybe this is the way to... Okay, anyway, it's an interesting question to push things even closer together, and let me end with this question, and happy birthday, Nati.
Speaker would be Noga, Alon. We'll talk about Nati communication and radio networks.
Okay, thanks. Thanks for coming. It's a great pleasure to be here. Birthday conferences are always nice, and this one is especially nice. I don't know if all of you noticed this new trend that in the old days they used to celebrate birthday conferences for kind of old people. And in recent years, they started to do it for young people, right? So I don't, but I can live with that. So the choice of the title has to do with communication. And indeed, one of the very many strong points of Nati has to do with his communication skills. Now, probably in the last lecture today by Michal, we'll hear about more of the strong points of Nati. Unless Michal wants to speak about his weak points. I'm not sure.
40 minutes.
It's yeah. I was going to say that then it will be a very short lecture, but you see, okay. So we will see about that. But indeed, Nati, so his communication skills, you often see it, so it often happens in lectures that someone is asking to translate a word from, or a phrase from Hebrew to English, or from English to Hebrew. And Nati would almost always would be the first one to suggest a perfect translation. But I'll give you a more specific example. So once Nati and Michal were visiting us in Tel Aviv, and my daughter Narkis was just studying for her psychometric exam. And she was going over all the Hebrew words and phrases, and Nati was explaining everything. And one thing that in particular that I remember, I never knew it, I wonder how many of you heard it before. So this was the origin of the word medocha in the phrase לשבת על המדוכה. Now I'm sorry, I cannot translate it to English. I'm sure Nati can, but I'll not ask it. So you know the phrase לשבת על המדוכה, and the question is, what is this word medocha and why is it used in this phrase? It's I'll mention some other questions in the rest of the lecture. But okay, so indeed this is also about communication, but here the lecture is about a more technical communication. So this will come later. There will be, okay. And this is a communication problem that has to do with radio networks. And I'll mention, I'll tell you some new results about this. This is a model that many of the questions and the initial results there were started by Nati and his collaborators. And I'll tell you two in fact recent results. One is from last year and one is from next year, in the sense that it didn't appear yet. And here is the outline. So I'll describe the model, just the radio model. And then I'll tell you these two parts. So one will be shared communication channels. And the second part will be about broadcasting. And then there will be some open problems. I just realized that I'm not sure. So we started 10:25. I should plan.
10:30.
Okay, so something 11:20, 11:15. Okay, good. All right, so let me tell you first this radio model. So this was introduced almost 30 years ago, and recently it has been studied quite a lot, because this is supposed to capture the mathematical aspects of wireless communication. But I think I'll be mostly interested in the combinatorial problems that it raises, and it's related to many interesting questions in combinatorics, in probability, and in information theory. Okay, so here is this model. It was introduced by Klamtach and Kutin. So we have communication, and communication is happening in synchronous rounds. Okay, Now we have a network, and it's best to think about this network as a graph. So two vertices that can transmit or receive are sitting on the vertices, and they can transmit or receive from each other even only if they are connected by an edge. And now in each round, each node or vertex can decide if he wants to send. I'll always try to denote the senders in red and the receivers in blue, or he wants to listen, and then he can receive something, and then he will be blue. And then the model is such that a listening node receives a packet from a neighbor in a given round if only one of its neighbor is transmitting at that round, and it's this neighbor, right? So if two or more neighbors are receiving at the same round, then there is interference, and somehow you don't hear anything. So this is a model, and indeed sometimes transmission collide, and you have problems. I switched recently to a Golan, and since then my messages always collide, but on the other hand, you pay very, very little. So you never speak, but it is very cheap. Okay, so here is just a picture to show how it works. So here is a network. This is a cycle of length 5. And suppose that the two who are transmitting are in red here. Then the two who will receive, if they decide to listen, are these two, because you see that each of them has only one neighbor that is transmitting, and because of this, they will hear, while the other guy, the one on the right, there will not hear anything, even if he listens, because two of his neighbors are transmitting.
So you transmit simultaneously to all of your neighbors.
Right, yeah. So you don't have a choice to whom you transmit. It's a very good question. So when you transmit, it goes to all your neighbors.
And you're either transmitting or listening?
Yeah, and you are either transmitting or receiving in each given round. And then you can, right. Like this morning, we both tried to transmit together, and therefore we didn't hear each other. Right. But this is, okay. So I should maybe mention that this is my most sophisticated animation. So let me show it again. Yeah, so this is, okay, that will be all right.
Can you go back?
Right. Yeah, okay. Okay. So there will be these two main parts. And as I said, one is from last year, and one is from next year. So this will be the older one, and this is a joint work with Ankur Moitra and Benny Sudakov, and it has to do with shared communication channels. So let me tell you what this is. So it's an example of a radio network, and indeed there our starting point was from a paper of Nati with Tzachi Birk and Roy Meshulam. I'll come to that. But let me describe the model. So a shared channel now consists of n sources, Si. So again, they will be red, and now they are only transmitting. Okay? And we have n destinations or n receivers, Tj. Now, source Si has to transmit some message M sub ij to destination Tj. And all the messages are distinct, let's say. So we have n squared distinct messages, and the message Mij has to arrive from source I or Si to destination Tj. Now, the way we want to implement it is the following. So we want to construct several, hopefully not too many, interconnection networks. So they will be, it's good to think about them as fixed wirings between the sources and the destinations. So I denote them by G sub P. Okay, P is an index. And I don't want to have too many of these P's, hopefully. So each G sub P will be a bipartite graph, which tells us which connections we have. And the vertex classes are S, the red transmitters in one side, and T, the blue receivers on the other side. So S, I call them here sources, and T, destinations. And then a message transmitted in this graph G sub P by SI, it reaches, again, as in the radio model, all the destinations Tj to which it is connected. Okay? And a message Mij is received successfully by Tj, so he really hears it, if indeed it is being sent in this round by Si, and no other source connected to Tj transmits in this round. Okay, so this is, and if you think about it, this means that the messages Mij received successfully in a given round, they form an induced matching in the graph. I'll soon have a picture, actually, a few pictures, but let me just remind you that induced matching is a matching, namely a set of edges in a graph, so that no two have a common endpoint, and they are induced. There is no other edge of the graph with two endpoints that are saturated by this matching. So, for example, the red, well, it's hardly red here, but it's supposed to be red. The two red edges that you see here, they form a matching, and this matching is an induced matching, right? Because there is no other edge with two endpoints that are covered by these red edges. But if I change, for example, this horizontal red edge to the very bottom edge, it will not be induced anymore because of this vertical edge, right? So this is an induced matching. And induced matching, the definition is as simple as that of a matching, but combinatorially, it's much more complicated to understand it. For example, the complexity, so the problem of finding or approximating the maximum size of an induced matching in a graph is hard. It's essentially as hard as approximating the largest clique, so this is very hard to approximate. While matching, of course, we can compute polynomially. So just a picture showing why these induced matchings are coming. So again, we have these red transmitters and dark blue receivers. And again, I guess I should say for the younger people in the audience that what you see in the picture are communication devices we used to have in the old days. I'm sure some people still remember them, like Nati, and so we used to call them telephones. There was and you see that here. Yeah, that's right. Yeah. So this is, and again, maybe it's kind of hard to see here. Can you see actually that the red is different than the? Yeah, you see the. Okay, from my. Right. No, that the red edges are different than the. Okay, yeah, because somehow from here it all looks the same color. But so you see that these two red edges that you see here, these form an induced matching, and indeed this means that in one round we can transmit these messages, right? Because we tell this guy at the bottom here to send the message addressed to this guy, and this to send the message addressed to this guy, and they will both hear them because nothing interferes with each other. Whereas if we will try to do this, these two red edges that you now see in red, then it will actually not work because it's not an induced matching, right? So you see that there will be interference. This receiver who is second from the bottom will hear two things and therefore will not be able to, or will get two things and therefore will not be able to receive any message successfully. Okay, so this has to do with induced matchings. And because of this, it follows that for the communication problem, our objective is really to cover the complete bipartite graph with n vertices on each side by a small number R of graphs, of subgraphs, G sub P, so this will be the different networks, so that each G sub P, we will be able to cover it by a small number of induced matchings. Because then we will be able to send the messages corresponding to all the edges of this G sub P by going over each induced matching in a single round. Right? And this is what we want to do it. So really the combinatorial problem here is, again, we have the complete bipartite graph. We want to cover it by a small, and the small could be even 2, maybe, by 2, 3, 5 bipartite graphs, so that each of them is a union of a small number of induced matchings. Let's see what are the trivial bounds that exist here. So for every R, no matter how many graphs GP we take, then the total number of required induced matchings is definitely at most n square, because we can always take every single edge, and every single edge is an induced matching. So all of them together, it's n square, and it doesn't matter how we divide them. So for this, we don't have to do anything. We can do it even with one graph, G, which will be complete bipartite, and then every, okay. And then on the other hand, an obvious lower bound is that for every R, the total number of induced matchings is at least n, because if you simply look at all the messages that emanate from one given vertex, so just all these messages, he cannot send more than one message in a given round, right? So, or if you want it in the combinatorial setting, all these edges are n edges, and they all are incident with each other, so no two of them can belong to the same matching, even if it's not induced. So all of them come from different matchings, so we need at least n. And in fact, if we know something about R's, then this can be slightly improved, but let's not worry about this at the moment. So what can be done? So in fact, this model was considered by Tzachi Birk and Nati and Ro'i Meshulam. And it's frightening to see that this is 20 years ago, because I remember talking with Ro'i about this at the Technion. It was not so long ago, really. I mean, we were kind of, okay. And the nice thing that they saw that indeed you can do something non-trivial. It's not clear at all that you can gain anything, right? And they have some nice combinatorial constructions that show that for R graphs, so of course with one graph you cannot do anything, right? If you have a complete bipartite graph, the maximum size of an induced matching in it is one edge, because every two edges are not induced, and therefore you need n square. But if you have R graphs, like 2 graphs or more, then you can gain some logarithmic power, at least, okay? And the question is, what can you do better? And this is what we could do with Ankur, Moitra, and Veni Sudakov. So for R graphs, the total number of required induced matchings in all the networks together, if we do it cleverly, it does not exceed n raised to the power 1 plus some constant 1 over log R. So, so at least this is something that for fixed R, fixed large R, it approaches the lower bound, which is close to n, right? So it will go down all the way to n. And even we checked what is the best that we can do for R equals 2. So the best construction will give that the number of induced matchings will be roughly n to the 1.94. And I should say that there is some observation by Ro'i that gives some lower bound, and the lower bound for R equals 2 is n to the 4/3. So there is still quite a big gap, but this is what we know. And let me tell you about the combinatorial constructions that comes into it. I'll not say much about it, but I want to. So really, this is what this is the main combinatorial thing that we need to get this result. It is the following. So for any fixed epsilon, one can cover even the complete graph. So it doesn't matter. We need it here only just for the complete bipartite graph, but we can actually cover even the complete graph on n vertices by some constant that depends on epsilon graphs, gi, before they were gp in the bipartite case, so that the edges of each gi can be covered by a small number, so only n to the 1 plus epsilon induced matchings. And yeah, the picture is supposed to somehow So this is supposed to be surprising, but let me maybe tell you, it's related to the following. So the same construction gives the following, which maybe sounds even more striking. And I'll try to convince you that it's counterintuitive. So there is a graph on n vertices, which is almost complete. It's nearly complete. It really contains 99.99% of all the potential edges. Has 1 minus little 1 and choose 2 edges. So it's almost a complete graph. And still it is the edge disjoint union of induced matchings. Each of them is of size at least n to the 1 minus little 1. So very big induced matchings, right? So if I say it kind of qualitatively, it says that we have, or without the numbers, it says that we have a nearly complete graph, which is the edge disjoint union of nearly perfect induced matchings. You see, if we have a complete graph, the largest induced matching it has consists of 1 edge. Cannot have even 2 because it's complete, so everything is connected. And the claim is that if we just delete a very, very small number of the potential edges, then we can already find there these huge induced matchings and cover everything by a small number of huge induced matchings. There was this picture here. See, whenever you take such a big induced matching, then there are all these edges that are missing here, right? So the induced matching contains a few edges, or some edges, but all the, if it has t edges, then there are these t square, or some constant t square edges that are missing. So for each induced matching, we will have lots and lots of edges that are missing, which gives you kind of the intuition that most of the edges are missing in this graph and are not, but somehow there is a way to put them together, and most of the edges are not missing because the graph is nearly complete. Okay? So this is, and then indeed, if we plug it in this communication problem, it gives the bounds that I mentioned. And I wrote something about the proof. So what I wrote here is that they combine some geometric tools based on measured concentration in high-dimensional Euclidean spaces, some probabilistic methods and techniques from the theory of error-correcting codes. Then I realized that you more or less can write the same statement on 50% of the proofs that appear in papers. So let me, here I don't want to describe anything about the proof, but I just mentioned that it borrows ideas from an old construction of Behrend, of dense subsets of the integers 1 up to n, with no 3-term arithmetic progression, and then from a well-known paper of Ruja and Semredi, which uses this construction of Behrend to get graphs with some similar properties to the ones that we're looking, and to an even more recent related paper by Jacob Fox and Posh and Law. But that's the only thing I want to mention about the proof. And let me move to the second, the more recent part. And that's again on the radio model. And again, it will be related to some old papers of Nati. And this is a joint work with Mohsen Jafari and Bernard Hauptler and Majid Kabazyan. So again, we will be in the radio model. And here's the problem is a broadcast problem. So we have one source node. And this node has k messages that he knows and nobody else knows. And he has to broadcast all these k messages to everybody else in the network. So you have to tell everything you know to everybody. Okay. And let's say that each message is some message of b bits. So it has some size, it's a packet. And the goal will be to deliver all the messages to everybody, and we want to do it in as few rounds as possible in this radio model. And we'll want to consider 2 ways to do it. So the first one is a routing algorithm, which means that every packet that you have, every message that you have, you can send it or not send it, but you are not allowed to mix messages. Whenever you have, in each round, if you send something, you send one of the original messages you had. Okay, so this is one. And the other one is network coding. So this was something that was suggested by Alswede, Kai, and Jung almost 15 years ago. And this enables us to take packets and to mix them. So to take some functions that are functions of the bits in maybe several packets, maybe even all the packets, but still we want that every single message will still be of v bits, right? Because otherwise we can just put everything together and send it all in one round, so then it's not interesting. Okay. So, so this is a broadcasting problem, and I'll call the broadcast throughput, so this will be the number of messages that can be transmitted to everybody per unit time from a given source. So I wrote here this notation, TRGS. I'll not use this notation, but just to mention that these are the two quantities that I want to consider. One of them will be the throughput via routing, so T sub r of GS. So this is from the source S, and this throughput will be a fractional number, right? So if it's 1 over 100, it means that on the average I need 100 rounds per message. Of course, I always need at least 1 round per message because it has to go out of the source. And the same will be TNC. This NC stands for network coding. And we want to compare these two throughputs. We know something about it, but we still don't really understand what's going on, so I'll try to tell you. And there is a simpler, a somewhat simpler problem that is essentially equivalent. So let's call it the bipartite broadcast problem. So now the network is a bipartite graph, sort of similar to what we saw before, with vertex classes S, the red senders on one side, and R, the blue receivers on the other side. And we think about it that all the vertices in S, they already know all the messages, and they have to transmit them, to convey them to all the vertices in R. Okay? And somehow there is a simple observation that basically considering this bipartite case is the same as considering the general case. So what I wrote here is that for both routing and network coding, the worst case optimal throughput on an n-node bipartite network is essentially equal to the worst case optimal throughput on general graphs with n nodes. And this is by essentially pipelining. So you really look at the source and you look at a BFS tree from it. So you partition the vertices to classes according to their distance from this source. And then really to transmit everything from the source to everybody, the information has to go to the first layer, and then from the first layer to the second, from the second to the third, and so on. And really, if you know how to do it from each layer to the next layer, then this is essentially the problem, the same problem as to transmit it to everybody. So maybe it's enough. So we'll consider only bipartite graphs. This has been done also in the old papers on the subject. So let's think first about broadcasting one message. I'll be interested mostly in many messages, but let's first think about one message. It's still quite interesting. It's called a bipartite network uniform if all receivers have roughly the same degree. So all the degrees are between D and 2D for some D. So from the receiver's side, all the degrees are the same. We don't care so much about what happens in the transmitter side. So there was a paper in the 91 by Reuven Bar Yehuda, Oded Goldreich, and Alon Itai. And what they showed is that that essentially constant log and round suffice for any uniform network with n nodes in each side, let's say. And because of this, so we can handle separately every degree, and then it will follow that log square n round suffice for any n nodes bipartite network, even if the degrees are very different from each other. And somehow it looks wasteful, maybe, to handle separately every degree. But what we showed with Nati and Amos Barnoy and David Peleg is that both the log n and the log square n rounds are tight for some networks. Right? So there are networks that indeed you will need. And just to say something about what's going on here, so both the upper and the lower bound, so we put it together. So essentially, the algorithm for uniform networks, so let's say that you have networks in which a bipartite graph in which every receiver has degree roughly 2 to the I, okay? Then somehow it makes sense that what you will want is to ask a set of senders. Now we have only one message, right? So everybody that will send the same message. So you ask a set of senders of cardinality roughly n over 2 to the I, or equivalently you could say choose a random set of senders by picking every sender to belong to this set with probability 1 over 2 to the I. If this is what you do, then for each receiver, the probability that in your random set exactly one of its neighbors will transmit will be a constant, right? Because kind of the expectation is 1, and this is a simple computation. So it means that a constant fraction of the receivers will actually receive the information, and therefore if you choose, you do it iteratively, or you just choose log n sets randomly, then with high probability it will be okay. So I don't know if this makes sense, but just says this is like a simple exercise in application of the probabilistic method, that if you have any uniform bipartite graph like this, you can always choose log n subsets of the senders so that for each receiver, in at least one of the subsets, he will have exactly one neighbor. Therefore, he will get the information. In the lower bound, so that's in the paper of Nati and his collaborators, the lower bound is somewhat more complicated. And the nice thing is that it shows that really transmissions aimed at 1 degree range are completely useless for the other degrees. So they really don't help you. I mean, a few receivers will still get this information even if they are not of the right degree, but most of them will not get anything. Either they will get interference because too many of their neighbors transmit, or they will get no information because none of their neighbors transmit. So somehow this log square is tight. Okay. Now we want to understand what is happening when we are broadcasting many messages. And let's first talk about network coding. So when we are allowed to send functions or linear combinations, it's enough linear combinations of messages. So the first theorem that we are going to prove next year in this paper is that for uniform networks in large number k of messages, again, it's uniform networks, so each receiver has roughly the same number of transmitters that is connected to it. Then the situation is very good. You have to send only constant k messages. Again, in the network coding model, when we send linear combinations. And because of this, for general bipartite networks, you can send k log n messages. So for each degree range, you will do it separately. And in this case, both bounds are tight. So of course, the O of k is tight up to a constant factor because you need k for uniform networks, and also for different degrees, indeed, you need this log n factor. So it means that the throughput, the worst case throughput with network coding for uniform networks is constant. And for general networks, it is constant over log n, right? So you kind of, in each round, you get a fraction of 1 over log n of a message. Okay. And then we want to understand what happens about routing algorithms. So it seems that there are 2 alternative possibilities here. I wrote them as questions here. So sometimes when communication becomes very long, things become more efficient. And then maybe it's possible that routing algorithms will be as efficient as network coding when we have to route many messages. So it will be k for uniform and k log n for non-uniform. It's one possibility. Another possibility is that maybe routing algorithms are worse, that network coding helps us. Maybe they are even as bad as in the case of k equals 1, in this paper of Nati et al., that you need a factor of log square n. So to convey k messages, maybe you will need k log square n rounds altogether. So these are the two questions. And usually, if at this stage of the lecture you ask a question, then the answer is usually no. That's my experience. But if you ask two alternatives, then, well, the answer is still no. So both of them are really wrong. And what is happening is quite strange. And I'll tell you what we know, but really, we still don't really understand what's going on. So here are, so this is a second theorem in that paper. So there are uniform n-node bipartite networks. So you have n vertices, n receivers, n transmitters, and all the degrees on the receiving end are the same. Even they can be n over 2 if you want, all of them. But so let's say they are the same or about the same. And the broadcast throughput of any routing algorithm here will be at most constant over log n. Okay, so we still have to, for uniform networks with the network coding, the throughput was constant. So for k messages, we only need k. Here we will need k log n. And also, this log n is tight for uniform networks. So for any uniform network, if the degrees are roughly the same, then always there exists some routing scheme with throughput constant 1 over log n. So for uniform network, there may be a log n gap between network coding and routing, and this is tight. You notice this is, so somehow you have this uniform network. By the argument we said before, if we choose the senders correctly, then we can easily make sure that a constant fraction of the receivers will get some information in every round. So if you are a typical receiver, you get a message every third round, let's say, but somehow, for some reason, even if the number of messages is very, very big, then inevitably, no matter what we do, you will inevitably get the same message many times. So on the average, you will get every message log n times, although you want to get it only once, which is somewhat, and this log n is tight. Okay? On the other hand, if you ask about what is happening really in the worst case for general networks, then actually there it's as efficient as with network coding. So for any n-node bipartite graph, there exists a routing scheme with throughput constant over log n. The number of messages will have to be very big for this. But, so it means that in the worst case, network coding does not really help you, or maybe it helps by a constant factor. Okay, I'll tell you something about, so just one thing about the proof, which is kind of a crucial lemma. So this has to do with what we call solitude transmission schedule. So we want something that will enable us somehow to look at all the messages together is too complicated. It's very hard to understand what's going on. So you want to be able to focus on one of the messages and to understand it. So this is something that enables us to focus on one message. So what is a solitude transmission schedule? It's the following. So it will be, so again, we have this bipartite graph with senders and receivers. And this will be a sequence of pairs, I sub r and A sub r, where IR is a sender, always, and it transmits, so it's good to think that it transmits in round R. AR is a set of senders that contain IR, but all of them, besides IR, what they transmit is just noise. So it only really cares, only real messages coming from IR. The other guys can only interfere, right? So this is okay. And we say that this solitude transmission schedule, STS, covers the graph if for every receiver there is some round R in which he gets the information, namely its only neighbor in A sub R is this IR. So some of his neighbors transmit, and you see that the guys in AR transmit noise, And we want that the only neighbor of him that will transmit in that round will be the one who transmits the real message. So we want that in AR, his only neighbor will be IR. And then we define the weight of this solitude transmission schedule, and this is a sum over the rounds of 1 over A sub R. So somehow if lots and lots of vertices transmit noise, then this has a low weight because it's kind of hard to hear the information. And okay. So, and there is this lemma that is kind of the main technical tool, and its first part is not surprising. The second one maybe is more surprising. So again, we have this bipartite graph, and the claim is that if there is a routing schedule for this H with throughput at least x, so x is this fraction, 1 over 10 or something, then there is this solitude transmission schedule that covers H, and the weight of it is at most 1 over x. So if x is relatively big, only 1 over 10, let's say, then the weight is not big, is 10. And in some sense, the converse is also true. So that's the more surprising part, and also the more difficult part to prove, is that if there is a solitude transmission schedule with weight W, but now we need not only that this transmission schedule covers the graph, but that a random permutation of it is likely to cover the graph. So random permutation of it, I think it's easy to understand. It's intuitive to understand what it means. We just apply the same permutation to all the sets in this transmission schedule. And if this random permutation covers with probability P, then there exists a routing schedule with throughput P over this weight. So if P was close to 1, then it would be like in the upper bound. And I should say that for the proof here, we don't know if it's required, but for the proof here, the number of messages has to be very big. So the number of messages for this to hold has to be at least n factorial. But once it is bigger than n factorial, then we are fine. So there is this okay. So I won't say anything about the proof of this, but let me show you why it is useful. So let's say the upper bound. So let me show, for example, and this will be very simple, why using the lemma, it implies that for any bipartite network, H with n nodes in each side, there exists a routing schedule with throughput 1 over log n. So to convey k messages, you need only k log n messages, just as was the case with network coding. You don't lose, okay? And this is why. So this is because if you look at the following solitude transmission schedule, so look at n pairs, and this will be always R in the set 1, 2, up to R. Okay, so this is it. Now I claim that these, forget now the random permutation, this set of pairs, it covers the graph H, because whenever you have a receiver, he has a set of neighbors, a non-empty set of neighbors. So there is the first neighbor in his set, and if you call this first neighbor R, then in round R, indeed, his only neighbor that will transmit will be R, because it's his first neighbor, or the others are A. And the same happens for any permutation, right? Because for any permutation, there will be the first neighbor according to this permutation. And the weight of this is just the harmonic sum, so it's sum of 1 over R. This R goes from 1 to n, so this is log n. So if we leave this lemma, then indeed it gives us this result if the number of messages is big enough. And it's more or less the same to show, so I chose here a special case of a uniform network, because that's somewhat simpler than the general case. So we have a bipartite network with n nodes in each side, and let's say that the degree of each receiver is at least n over 4. So it's between n over 4 and n. So every receiver has a big degree. And now the claim is that there exists a routing schedule with throughput constant over log n. So I told you that something like this holds for any uniform network. And again, here, the set of pairs we take are the same pairs as before, R and 1 up to R, but we let R just to go between 1 and 10 log n. And the thing is that if you take a random set of size 10 log n, then with high probability it intersects every set among the set of neighbors of the receivers, because each of them is of size n over 4, and we have only n of them. So it means that for a random permutation of this, then this set will intersect it, and then again there will be the first one that will intersect it, and then this round will be successful. Now I know it's probably impossible to follow, but that's simple. And if you do the computation of the weight here, then it's a harmonic sum, but only as r goes up to 10 log n. So this will be a log n. So this is basically what I wanted to show about the proofs. The main thing is, of course, to prove this lemma, and I'm not going to talk about this. Let me mention just the open problem. So it seems that on both these topics that I briefly described, the shared communication channel and the broadcasting, we understand it a bit better now. So both were initiated or first considered in these papers by Nati and his collaborators. And maybe now we understand it better than we understood it, say, 3 years ago. But still, in both of them, there's still a lot that we don't understand. And, and in particular, for the shared communication channels, what I mentioned here is that suppose the number of rounds in a network with n senders and n receivers is n to the 1 plus epsilon. You remember that we could get close to n to the 1 plus epsilon with some c of epsilon networks. Yeah, I should have said the number of networks, G sub p. How many graphs G sub p are needed? And we know that it's some function that depends on epsilon, but this function, as a function of epsilon, the bounds are between log of 1 over epsilon and something exponential in 1 over epsilon. So really, there is a double exponential gap here between the lower and upper bound. If you care, I mean, the progress was to show that for any fixed epsilon, it's a function of epsilon only that does not grow with n, but which function it is of epsilon, we are very far from understanding, and it will be nice to know it better. And for this broadcasting problem, it will be nice to understand what is the gap, what is going on. So what is the gap between network coding and routing for relatively small values of k, when the number of messages we have to broadcast is not so big. So for k equals 1, we knew what it is, right? So we understand there everything exactly. And it's possible to show that somehow, using some entropy inequalities, you can show that that the gap between network coding and broadcasting is at least log n over log k for some carefully chosen networks. And this will give some non-trivial bound for any k which is less than, significantly less than a polynomial in n. But we have no idea what happens for k equals n, or for k equals root n, or for k equals n to the 100. And it will be nice to understand this better. So with this, let me finish and say happy birthday again.
Questions?
Let me just say I'm not representing any funding agency, but still I would be curious, is there any connection to anything really used anywhere?
Right, yeah. Yeah, it's a tough question. So I think I suspect that in the original, in the what I call the channel communication, so this, I suspect that this is not close enough to wireless and probably is not relevant to anything.
You know you're being recorded if you want to score next
Right, yeah, but the second thing, so this broadcasting thing, so this is this, I think, could be relevant for something. I mean, of course, the weak point here, and for that reason, it would be indeed nice to understand what is happening for small k, because if many of our bounds or algorithmic constructions are for k, which is n factorial, so I'm not sure how many people use Cellcom now. Maybe they have in Israel 3 million or something. So the factorial of this is a big number, right? So it will be nice to understand. But I think that this could possibly, maybe, have some potentially not impossible applications. But okay. And I'm, right.
More questions? So let's thank Noga again. I'm sure that among all the people here, I have the longest Nati experience. We met as almost children, as teenagers at the age of 15. We both participated in the chess championship of Haifa. Later we were schoolmates, not classmates, but schoolmates. So if anybody wants to know how was child Nati, I can tell you. But I'm afraid that I have nothing spectacular to tell. He was the same Nati then, I mean, cheerful and of course bright, and mainly with the same sense of humor. I remember having been impressed already then by his sense of humor. And later we studied at the Technion together with Mickey, and this is today's the reunion. And somehow we all ended up in Combinatorics, which probably isn't a coincidence. Probably it's Nati's influence. I mean, I resisted for longer than the others. I came to Combinatorics only later. And thanks to Nati, I remember coming to Jerusalem in the early 80s, staying with Nati and Michal, and learning my rudiments of finite combinatorics. I was then. So, congratulations. Okay. Now, by way of clarification, the title doesn't mean that we are going to solve the odd case, the case of n odd in Rota's conjecture, whatever this conjecture is. I'm going to tell you what it is. It's more like the curious case of Rota's conjecture. And let me start with presenting the protagonist of the talk, which is called independent systems of representatives. These are something that appear in many branches. And in our context, it is the independent refers to linear independence. So you have matrices, say A1 up to AN. We'll take them n by n matrices, say. And we want to choose columns, one from each, that are so these are the representative business, and we want the representatives to be linearly independent. This is called an independent system of representatives. And let me start with a very simple observation, which is that if your A's, if your matrices are non-singular, then they have an ISR, independent systems of representatives, which is you just do it greedily. You choose one from the first, any column from the first, and then it doesn't span all the columns in the second because it's linearly non-singular, the second matrix, so you can choose another. And these two don't span all vectors, all columns in the third, so you can choose and continue and choose inductively. Now, when you have such a simple observation, it could probably be strengthened in some way. And there are two, perhaps more, but at least two ways in which this can be strengthened. One is that you want to do two at once, two systems of representatives for two systems of matrices. So you have A1 up to AN and B1 up to BN, and a joined system of ISRs is that you choose columns with the same indices in the same places. Okay, and you want to achieve that. And the conjecture is that you can. Okay, so you can choose joint representatives for two systems. Unfortunately, it's false. So here is the not so complicated counterexample. So these are the top are the AIs and the bottom are the BIs. And if you choose this column, then you cannot choose this column because this will not be independent from this, and you cannot choose this column because this will not be independent here in the BIs. Okay, but possibly it's almost true, which means that perhaps if you have two systems, then you can choose representatives for almost all, for n minus 1 of the matrices. This is a conjecture. It's not I didn't write it as a conjecture. 1 minute, I have to see, perhaps I've skipped a slide. Because, yeah, okay. Page up, 1 minute. Okay, so this is a conjecture by myself and Eli Berger, I forgot to mention that.
Is there some similar thing when you take A1, B1, and C1?
Then probably you have to go down to half n.
Half n?
Probably, yes. Okay, now this is a hopeless conjecture since it implies very famous conjectures from the 70s about, so a conjecture of Reiser about Latin squares. But probably this captures somehow the essence of that Reiser's conjecture. Hopeless at the present time. Sorry? To refute? Okay, perhaps, I don't know. Having made this conjecture long ago, I tend to believe it by now. But of course, if you come up with a counterexample by the end of the talk, I'll be happy. And
this is really beautiful conjecture.
Okay, thanks. And, okay, you're welcome to work on it. Okay, so this is a conjecture. And here is a special case. Suppose that the BIs are related to the AIs. Okay, there are AI minus 1 transposed. Then there exists a full for n, not n minus 1. And why do I care about this? Because we shall need it in some sense. So TBU means to be used at the end of the talk.
For cellular networks.
Yeah, okay. Okay. So there is another possible strengthening. So we said that the basic observation is that there is, when you have n non-singular matrices, then you always have one ISR. And the other possible strengthening is that there are many ISRs, okay, not just one. In what sense many? This is a famous conjecture of Rota from the 70s. Many in the sense that you can decompose into them. So you have n matrices. Let me have it. So
many people complain that they don't ask questions, and now I cannot.
Okay.
What about really many in the usual sense of the count?
So, for example, by the green, many in the usual sense, so every column that you have participates in one, because you can start the greedy with this. Counting, never thought of counting them. Yes, okay, n factorial.
Small numbers.
Yes, these are huge things. So, I don't know. Good question. Okay, so here is the conjecture. So this is the main conjecture I'm going to talk about. That if you have n by n non-singular matrices, then you can decompose, you have n square columns, all in all. You can decompose them into n ISRs, independent. So you can rearrange them in n matrices so that every matrix, non-singular matrices, so that every matrix is an ISR, namely consists of one column from each. Okay. Now, there is a generalization by Jeff which is a two-dimensional. Okay, kind of. So here is the conjecture of Jeff that an n by n array of non-singular matrices, so you have n square matrices this time. Here they are. And then you can have a two-dimensional ISR. What is a two-dimensional ISR? You can choose one column from each of those matrices so that in every row and every column you have an independent set of vectors. Okay? So if you look at... Yes. So if you look at every row and every column, you see an independent system. Now, if you if you have a Rota system, A1 up to AN, and you repeat them n times, then it's easy to see that Jeff's conjecture implies Rota's conjecture, where the decompositions are the rows, so of the red ones. Okay, you cannot repeat the same from, you cannot have two equal columns in every column of this matrix. Okay, so this is a generalization. And it's interesting because this generalizes also a famous conjecture, theorem by now, of the conjecture was of Dinitz, and the theorem was of Galvin, which is the same when you have, instead of A11, you have n elements. In each place, in each entry of this big matrix, you have n elements, and you want to choose elements so that in every row and every column you see distinct elements. Okay, that was the Dinitz conjecture proved by Galvin. And this generalizes, of course, also this. And the one interesting point about it is that the Dinitz conjecture was the source, I think, of the invention of the Alon-Tarski conjecture. That's where you invented that, right? I guess, in that context. Yeah, in order to solve it. Well, it does solve it in the even case. And we are going to get to this Alon-Tarski conjecture. It's related also to this problem, to the Rota problem. Okay, now I want to mention another problem, which is scrambled Rota. What is scrambled Rota? Suppose that you take the matrices A1 up to AN, and before asking the question, Rota's question about the composition, you scramble them. Namely, you just scramble the columns among other n matrices. So what do you get? You get matrices that we still call them A1 up to AN, that you know that they came from, you can rearrange their columns in n matrices, non-singular.
What do you mean scramble?
You take your matrices and take the columns and just mix them somehow. All of them among n, redistribute them among any n matrices. Okay? So you get matrices that I still call A1 up to AN, but you know about this, that they came from n non-singular matrices, so you can rearrange them in n non-singular matrices. They're not necessarily non-singular, but their columns can be composed into. So what Rota asks you is you're given n non-singular matrices, and you're asked to scramble them in a certain way so that each of them is an ISR and non-singular. So now somebody does half the work for you. You already scrambled it. So it seems that it will be not harder now. So the question is, if they are scrambled, can you still do that? So question, if you have n matrices such that they are the rearrangement of n non-singular matrices, so you can find still an ISR, now non-trivial. You have to prove it. But you can find one ISR. Question, can you decompose?
So this is a more difficult question.
That's a more general question, more difficult and therefore it falls. But there is some point in it. Okay, so here is an example. So I take, the EIs are, say, the standard vectors of Rn. So A1 is just repeated E1 n minus 1 times, and then E2 minus E3, And A2 is E2 repeated, and then E3 minus E4, you see there. And this goes. This is after scrambling. So it's very easy to see that you can scramble. Why? That they originate in n square columns, that the n square columns can be rearranged in n non-singular matrices. For example, you can take the columns here. They're almost okay. If you take E1 up to En, that's obviously linearly independent. The last one doesn't go, because the last one has some 0, okay? But you can easily repair it, so move elements, and you can get it. Okay, and now I'm speaking about n odd. For n even, you have to do a slightly different construction. And now, suppose that you can decompose them into n linearly independent sets, then the right column cannot appear all in the same set. Cannot constitute one set because the sum is 0. So you have to distribute them among different sets. And since n is odd, at least one of these sets will contain non-zero many of the right, EI minus EJ from the right column. And less than half, right? Less than half of this set will be these guys. Now, they're arranged on a circle. And when they're arranged on a circle, and less than half are this, then there must be at a certain point on the circle and two elements, EI, EJ, and then somebody from this set of the right guys, right column guys. Okay, there must be, when you rearrange, when you have blue-red elements on a cycle and fewer red, then you must have blue-blue-red at some point. Okay, and this blue-blue-red is like this: EI, EPLI, and this. Okay, which are linearly dependent. So you cannot do that. Okay, actually I was surprised. I visited Kaiser now in Pilsen, and he mentioned an example very similar to this that they found with somebody else. Okay, but now the point is that this is almost okay in the same sense that we had before. You can find n minus, in this example, you can find n minus 1 disjoint ISRs, and you can cover by n plus 1, okay? And this is the conjecture. This is a conjecture. For general n, you can find n minus 1 disjoint ISRs and cover by n plus 1 ISRs. And this is a special case of a more general conjecture, which I like very much. It's an old conjecture about matroids. So whoever doesn't know what a matroid is, I cannot explain. Here it's an imitation of Rn, of independence in linear vector spaces. So suppose you have two matroids on the same set. Call them M and N. This is a common structure that people speak of. It's the subject of a famous theorem of Edmonds. And suppose that in the first matroid you can decompose into K, I wrote there, N independent sets. You can decompose the vertex set into N independent sets. And suppose that also in the second you can decompose into N independent sets. Now, in our case, in the Rota case, the two matroids are, of course, the Rn is one matroid, linear independence, and the other is the partition matroid into the matrices. In this matroid, a set is independent if it chooses no more than one column from each matrix. So these are the two matroids. So the case of scrambled Rota, believe me, think for a second, then this is about these two matroids. And the conjecture is that for the intersection, if you look at those sets which belong to the intersection,
They are independent in both.
Yeah, independent in both is precisely this joint ISRs. I want them to be both independent in the linear vector space and in the vector space, and one from each matrix, that you can cover by n plus 1 sets belonging to the intersection. This peculiarly has to do, this +1 has to do with Wissing's theorem. It's strange. There is a common generalization of this conjecture and the famous conjecture of Goldberg and Seymour, which is somehow almost Wissing's theorem. So I will not mention it. So the thing is that it pertains to something called two polymatroids. Two polymatroids is a concept that encompasses both intersection of matroids and, say, matchings. I will not say more, but the +1 is the same +1 that appears in Wissing.
Are you able to show that in other senses that the intersection is large?
Yes, so this is the next result. So you can cover by 2n sets belonging to the intersection. This is a result with Ellenberger, and the only proof known nowadays is topological. So you need topology for it, algebraic topology.
But there is a set that's
You can cover everything.
No, much easier to do. A set that's independent
And contains half of them. That's easy. That's trivial. Yes. Yeah. Okay. Now let's move to another conjecture, the Alon-Tarski conjecture. So everybody knows what the sign of permutation is, and I'll just denote it by 1 if the permutation is even, and -1 if it is odd. And the sign of the Latin square is just the products over all rows and all columns of the signs of the permutations. Okay. In a Latin square, every row and every column is a permutation. And let me denote by Ln, capital L, the sum over all Latin squares of the sign of L. And the Alon-Tarski conjecture is that it is non-zero for n even. Okay. Now, for n odd, it is 0. Why? Because when you permute 2 columns, you reverse, it's easy to see, but think for a second, you reverse the sign. And yeah, the signs of the columns don't change, but in n places, and n is odd, you have a transposition which changes the sign of the rows. And therefore, you have a bijection between even and odd Latin squares. And therefore, the sum of the signs is 0. So the conjecture is this. And it's known for infinitely many values. So for every prime +1 and every prime -1, it is known. And the theorem connecting the two things, the two conjectures, is that if one conjecture, the Alon-Tarski implies Rota. This was proved in the 90s already by Rota and Wang, a student of Rota, I think, and independently by Shmuel On from the Technion. And let me write you the On proof.
So you're saying that if the Alon-Tarski is false,
No. If it's true, then Rota is true. The opposite, I don't know. And probably the Alon-Tarski is true. So, I mean, numerically, there is very strong evidence. The number, this Ln goes to infinity very quickly. Okay. So, here is another protagonist of the talk, systems of permutations. Now, notice that a Latin square is a system of permutations. If you look at the columns, it is a system of permutations. And for a system of permutations and permutations, the sign is, of course, the product of the signs of this permutation. And the on observation is that a decomposition, like Rota wants, decomposition into matrices, is given by a system of permutations. So each pi I tells you how you distribute the columns of AI. They have to be distributed among the different BIs. We call them BIs, I think, before. So now we should call them BIs. So yeah, here is the BIs. BIs are the ISRs, the matrices after the rearrangement. So pi1 tells you how to distribute the elements of the columns of A1 and so forth. So each bi is this matrix. And on proved an identity, so I wrote again this formula for the bi's, and on proved an identity written below. Okay, you have to digest it in a second. So the sum over all permutations systems of this sine of pi times the product of this determinant, where the bi's are defined by the pi's. I just didn't want to load the formula too much, but they are dependent on the pi. If you sum it all, then you get ln, the Alon-Tarski number, times the product of the determinants of ai. Now, if the Alon-Tarski conjecture is true, then ln is non-zero, and the product of that determinants is, of course, non-zero because they are non-singular, so the right-hand side is non-zero. So the left-hand side is non-zero, which means that at least one term here is non-zero. So for at least one pi, this product of these determinants of the bi defined by pi is non-zero, so all these bi's have to be non-singular, which is what Rota wants, the composition into non-singular matrices. Okay, now this identity looks complicated. It actually is not so complicated if you use the right notion, which is something called hyperdeterminants. Now, hyperdeterminants are determinants of high-dimensional matrices. Okay, so we are going into higher order combinatorics here. These were defined by Kalai in the 19th century. So a tensor is just a matrix with many dimensions. Okay, so it has many indices, every element. And the hyperdeterminant is the sum over all permutation systems of this sign, of course, like in the ordinary determinant. And then you take this term there, the tensor. Tensor is that multidimensional matrix. And the elements pi1 of I, for every I, you take this pi1, pi2, all of I. And you take the product. If you think for a second, this is the ordinary determinant in 2 dimensions. Only that you do something a bit different, which is in 2 dimensions, you have just one permutation, right? So one of them you take as the identity. Well, the story is this. For n even, if you fix the first permutation to be the identity, you get the same thing divided by n factorial. So we are interested only whether it's 0 or non-zero, so it's the same. So, and for n odd, this is 0. Okay, so for n odd, you have to fix the first permutation to be the identity in order to get something interesting. Okay, so this is the hyperdeterminant, and the hyperdeterminant obeys the same rules as normal determinants. Namely, if you take a hyperplane and multiply it by 5 in this tensor, then the hyperdeterminant is multiplied by 5. You take 2 planes, 2 parallel planes, and add them, then add one to the other. You don't change the hyperdeterminant. It's just the same rules. Okay, so what does this have to do? First of all, formally it's similar to what On does, but I have to define something. So for a system of matrices A1 up to AN, I define a tensor, I call it T of A1 up to AN, by the following. So what is T of in such indices? You take these indices, take these matrices, and choose the columns by these indices. Okay, so you choose the I1 from the first one and I2 from the second two, and take the determinant. Okay, so this is the tensor pertaining to, and the left-hand side of On's identity. Well, since I don't have it here, but you'll have to believe me or remember, is just that. the hyperdeterminant. The hyperdeterminant is the sum over all permutation systems of something, and this is precisely what happens in On's identity. So this is it. And now something surprising. If you put I instead of the matrices, then you get precisely the Alon-Tarski number. And this is very simple. It's just, well, I will have to, if you remember, this is the hyperdeterminant. If you put I in all of them, then you're not allowed to have pi 1 of I the same as pi 2 of I if you want to get, if they are the same, it means that you chose column number, say, 3 from the first and column number 3 from the second. They're identical. Okay? So when you put them in the tensor you calculate the determinant, you get 0. Okay? So if you want non-zero, then you want all these to be different. Which means what? It means that if you put the pi's, the permutations, in columns, then all rows have distinct elements. All rows are also permutations. Now, what is a system of permutations in which every row is also a permutation? It's a Latin square. Okay, so it's not surprising. So the system of permutations in the case that you put I, it gives you non-zero here only in the case of Latin square. So this will give you some idea that it's not surprising that Latin squares appear here. Okay, and we have that. And now, I don't want to go to spend too much time on this. I'll just tell you that the On's identity is a special case of a more general identity, which is the following. Suppose that you take Tii and multiply this I, or any matrix that you have here, by some matrix B, say. What happens to the determinant? Answer, it's multiplied by the determinant of B. Okay? It's very easy. You do it by, you represent B as a product of elementary matrices, and for elementary matrices, it just follows from what I told you before, that hyperdeterminants behave like determinants. Okay? So what you do is you multiply this by A1, you multiply this by A2, and so forth, and what you get eventually is this hyperdeterminant of everybody, this, which is the left-hand side in On's calculation, On's identity. And what did you do? You multiply, when you multiply this by A1, you multiply it by the determinant of A1, you multiply this by the determinant of A2, and so forth. So there, on the right hand, you get the products of the determinants of the AIs. Now, I have to apologize for not having written it on the slides, and the reason is that I understood it only on the way on the bus to Jerusalem, that there is a very simple proof of On's identity. So again, I have to thank Nati for, I would have arrived without the bus, but okay, so let's continue. Now let's, I told you that I'm not going to solve the odd case, but I will say something about it. The motivation for all this work was trying to say something similar for n-odd. For n-odd, this On's approach cannot work because L of n is 0. But what people did was trying to find another parameter which is non-zero for n-odd. And it is this. You fix the first, so you look again at Latin squares, and you fix the first row and first column to be identity. Now you cannot do this trick of permuting columns because you got out of your class. And you define this small L of n, and hopefully it's non-zero this time. Well, here is an example. L of 3 is just 1 because there is just one Latin square with first row and first column identity, so there is no problem with that. And the conjecture is that it is always non-zero. Okay, so this conjecture was made independently by Stones, Wanless, and Kotlar. in relation to this, I mean, they're trying to solve the odds case of Rota's conjecture. And a theorem of Kotler and myself is that indeed, if this Ln is non-zero and n is odd, I forgot to mention it there, you need n odd, then actually you don't need n odd, because as I will tell you in a minute that if Ln is non-zero, then, okay. Then there exists n minus 1 disjoint ISR, precisely as in the scrambled case. So you almost have the conjecture, not n disjoint ISRs, but n minus 1. And in fact, so let me just go up. In fact, the thing is that you can replace this by the Alon-Tarski conjecture. So this is something with recent with Martin Lebel. So the theorem is that the two conjectures are the same. So the Stone-Wanless conjecture and Kotler conjecture about Ln and the Alon-Tarski conjecture are the same because, well, for n even, Ln is 0 if and only if capital Ln is 0. And for n odd, the non-zeroness of small ln is equivalent to the non-zeroness of capital L n minus 1. And in fact, there are formulas. So for n even, you have this. So obviously, one is the right-hand side is 0 if the left-hand side is 0. And this is trivial. This goes by permutations. The second is a bit surprising. It's a bit surprising mainly because the formula is so simple. So it says that the right-hand side, Ln, is non-zero if and only if the left-hand side is non-zero. The formula is very simple. The proof is not a simple bijection. We don't have, perhaps we are missing something. But the proof is very circuitous. And it uses alternating paths, which is interesting because I think it's the first time that alternating paths have been applied to the Alon-Tarski conjecture, as far as I know. I mean, nothing. And perhaps there is some interest in this method. Okay, so how do we prove the theorem with Danny Kotler, who is, by the way, here? We restrict the set of permutations. So we look at the permutations that in which pi 1 is the identity. Okay? The first permutation must be 0, the identity. And the theorem, again, is through some identity, a more complicated one than the own identity. So you can read it. There is no point in my reading it aloud. But the point is that if the determinants of the AIs of A2 up to AN are non-zero, and the permanent of A1 is non-zero, then you can take care that then this sum is non-zero. So at least one term is non-zero, and in this term, the n minus 1 BIs, n minus 1 permutations, matrices are non-singular. So you need here permanent of A1 is non-zero, but you can do with determinant of A1, which is what we have. We have only the determinant by some simultaneous row operations on all matrices. So this is the idea, and unfortunately, this as yet doesn't have a simple hyperdeterminant proof. This you have to work. And as I told you before, this pi 1 equals identity is somehow natural natural when you have hyperdeterminants, which we don't as yet have here. But it has some intuition why it appears there. Okay. Here's another approach, which is the following. So another approach to Rota. What you do is you first choose, as we said, you do something that we said is simple. You choose an ISR, an independent system of representatives, a column from each. Okay? This you can always do. And restrict your system of permutations in a different way, which is this. You look only at permutations satisfying this, that pi I of 1 is these precisely ji's, these representatives. Okay? And now we define something similar to On's expression. The sign of pi's times the determinant, the product of the determinants bi, but you sum only over permutations in Z satisfying this condition, and you don't take into account the sign of the first permutation. Okay, similar to the idea, the previous idea where pi 1 was the identity, but here we just don't take the sign of the permutation. Okay, and then you have another identity. You need A1 to be the identity matrix, which is not a big restriction, because you can always have, you can do simultaneous row operations on all matrices. This doesn't change the conjecture or the outcome, so you can do that. So A1 you can assume to be I. And then you have some complicated formula. But the main thing is that delta, sorry?
Thing 1 and thing 2 appeared already in the book by
Dr. Seuss.
Yes, I know. So, so on the left-hand side, you have the product of the determinants of bi. So if this is non-zero, then for one term of this, one term here will be non-zero, which is what you want. You want bi's whose product of determinants is non-zero. And here, the product of the determinants on the right is non-zero. And this is non-zero. And this we assume to be non-zero by the Alon-Tarsi conjecture. We know by now that it's equivalent. So we only have this thing 1 and thing 2 to take care of. So here they are. Thing 1 is this determinant. And if you remember, we chose J1 up to Jn so that this determinant is non-zero. Precisely that was our choice. We chose an ISR. Now, unfortunately, thing 2 is more complicated. It's, first of all, it involves this AI minus 1 transposed, okay, in the same columns, okay, which, if you remember from the beginning of the talk, we can assume that what? That they are independent, so the determinant is non-zero. But unfortunately, what appears there, so we can take care that this determinant is non-zero. But we want the permanent to be non-zero, okay? So if you could just choose the ji's so that both the determinants of these ai's will be non-zero and the permanent of this ai minus 1 transpose in the same indices will be non-zero, we would be happy. We would reduce the odd case of Rota to the Alon-Tarsi conjecture. Unfortunately, it's not always true that you can do it with a permanent. There's a very simple example in which you cannot do it. So the only thing we can say is the following. So this is not great progress. This is not something which is really pertinent. I mean, this condition that will appear in a second of non-negativity is not something really naturally pertinent to the problem, but this is what we can do. So, so this you know by now, this assumption, this Alon-Tarsi assumption. This you have to assume. And if the AI minus 1 transposed are non-negative, then if the determinant is non-zero, then also the permanent is non-zero.
Negative entry-wise.
Entry-wise, yes.
AI minus 1?
AI minus 1, yeah, but you can also do that. You can do that by reversing this. So this is also true. What I wrote is not false. I mean, not too interesting, but not false. Okay. I think this was the last. Okay. Sorry?
Alon-Tarsi number relative to the number of lattice squares?
You have the expert here. Two experts, actually.
Positive or negative?
They're always positive, non-negative.
We thought that maybe it's close to square root.
So it's like random.
Maybe. But somehow it's hard to compute those numbers even for n equals 8.
And another question, that you had hyperdeterminant, then is there also a hyperpermanent?
Yeah, you can define. I don't know how interesting it is. I mean, Nati works on such things and counting that.
It looks probabilistic almost, because you had the sum over sine of pi times the determinant of that system of representatives that you have. So it's like saying, let's go over all possibilities and the average product of determinants. But then you have the sum. So if it was a permanent, it would be exactly.
Yeah, there is interest, but apparently not interest related to Rota's conjecture. There you need the determinants, I think.
So Rota's conjecture is true for infinitely many cases because of Driscoll.
Yeah.
Was it known to be true for infinitely many cases before?
No. This is the only proof known. Actually, there is a more general conjecture for matroids of Rota. You don't have to take the vector space case. But for the vector for there, nothing is known beyond n equals 3. But for vector spaces, yes, the combination of these two results from the 90s, both, I think, gives you infinitely many cases of Rota.
More questions? Okay, so let's thank Alon again.